All right, so we are about to start covering more advanced stuff, high order stuff. I will gonna explain, but you need to make sure the first videos that I uploaded up to now, up to this video on the playlist, you need to understand well. And if you have any questions, please let me know. With this video, first I would like to summarize the key moments to remember from the previous YouTube videos and what is coming next. And if not, if you haven't, please subscribe. Several of you subscribed, thanks. Share these videos, this playlist with others who are interested. I am trying to cover the best of adaptive control. I have been doing this for many years now. All right, so these are some videos, right? One of the very first videos after the introduction video was to adapt or not to adapt video. And in this video, I wanted to highlight you guys, when you choose to adapt, you don't need to know uncertainty bounds. And so adaptation has better advantage as compared to the fixed gain control. You can achieve a desired performance with less knowledge about the uncertainty. So that was the key moment or key message that you need to get from this video. You can also, for every video, right, up to now, I also uploaded MATLAB examples. Then I mentioned two ways to do adaptive control when time comes to following a command: reference point versus reference model. And I mentioned in the theoretical video and then in its application in the simulation MATLAB example video that reference model is better. So let me put a tick. So basically, what to remember from this video is better adaptation performance with reference model as compared to reference point. So we choose to adapt, we choose reference model. When you combine these two concepts, we arrive MRAC model reference adaptive control. And then we covered some cases, right? For example, when you have time varying uncertainty, basically when W, the uncertain weight, is time varying, you cannot arrive V dot less than equal to 0 form. In this case, I introduced two highly adopted concepts. One of them was projection operator, other was leakage modification. Both of them are advantages in addressing the case when you don't have V dot less than equal to 0. So in other words, both approaches guarantee boundedness when you cannot arrive V dot less than equal to 0 without these modifications. Here is the projection operator based law. So we considered when you have time varying uncertainty. This was the control signal. This is the adaptation. This is the projection. Think projection has like a fancy saturation operator. We recovered some very important properties of the projection operator. This is the reference model. So we basically saturate W hat estimates to prevent them growing more than it should. And with leakage modifications, for example, sigma modification, you have the same system, time varying uncertainty, control signal, reference model. We just added this leakage term. So I would like to make in this video clear cons and benefits and advantages and disadvantages of both methods. With projection operator, right, you need to know some level of uncertainty upper bound. But this is not as strict as fixed gain control approaches that we discuss in this video. Sometimes people get confused about them. So for example, in order to achieve a better performance with fixed gain control methods, you need to know these bounds tight. If they are more tight, you have a better performance. However, with projection operator, if you don't know an upper bound on the uncertainty, if you selected 10 minus 10, maybe more, 100 minus 100. So the idea is to saturate the weight update. So you can be conservative here on the selection of the bounds. So it is not as bad as the fixed gain controllers conservatism. So you can be conservative, it won't affect your performance. Plus, if you choose projection operator, let's say you are dealing with a time varying uncertainty right here. Let's say after some couple of minutes, couple of hours, uncertainty stays constant. Instead of time varying, it converges to some constant values. In this case, if you are using projection operator, when Wt converges to some constant in time, you are going to recover asymptotic stability of the error. Error will go to zero as t goes to infinity. So that's the advantage. So again, advantage, you can record if you are using projection operator, and at some point, if this converges to a constant, then you are going to recover this property. But that was the advantage. Disadvantage, although a mild disadvantage, you need to choose some saturation, W max, W min, as I explained in the projection operator video. Now, in the leakage modification, you just add this term, and you don't need to choose an upper bound on the uncertainty, right? You just add this term, then you are done with it. So the advantage of leakage modification as compared to the projection operator, you are not choosing basically some W max, W min, right? You don't have some fancy saturation. On the other hand, the disadvantage of leakage modification terms is if Wt converges W at some point, you still have this term. So you will never able to you will be never able to going to recover the the performance. I mean, what I mean by error will never go to zero. Let me put it this straight. So if I compare these two, I like leakage modification personally because I don't need to choose any W max, W min, any fancy saturation. That's the way I like. But I also like projection operator because if this time varying uncertainty converges to a constant, then I will be able to recover asymptotic stability of the error dynamics. And since we don't need to select the W max, W min to be very tight, I kind of tied projection operator in applications of adaptive control, but both leakage modification and projection operator are fine. I just want you to be aware of these cons and pros about the projection operator and leakage modification terms. All right. So after these videos, I introduced you unstructured uncertainties. So you have uncertainties like this, well, you don't know the structure. So how you are going to write it, formulate it? So you need to select a basis function, right, for your adaptive controller. In this case, this state of X. But if you have no knowledge about the uncertainty, which can happen in many scenarios like complex aerodynamics, currently getting more popular applications like electrical vertical takeoff and landing applications, VTOL vehicles, you have complex systems. And when you have complex systems, you have complex uncertainties. At some point, you are going to deal with systems that are more complex than an inverted envelope. Inverted pendulum. As this being said, inverted pendulum can be a very complex system. And at some point in time, many years ago, one of my former students wrote a paper doing experiments. It took 6 months. So controls is not easy, but we are getting there. We are learning. Everybody is learning. None of the systems are easy, but there are a lot of uncertainties. But as the complexity getting higher and higher, we really need neural networks and neuroadaptive control. So that's why we have this universal function approximation theorem, which is the neural networks, right? We approximate functions. So after introducing you guys on the neural networks video, I introduced you neuroadaptive control. In neuroadaptive control, basically you parameterize the uncertainty like this. So to capture the uncertainties, basically this theta, the basis function, includes radial basis function in its elements. Likewise, in adaptive control, you use these radial basis functions. This is with the leakage modification, sigma modification. If you want, you can also use projection operator, because in these cases, because of this approximation error, you are not going to have v dot less than equal to 0, so you either need to use a leakage modification or a projection operator when you deal with neuroadaptive control. I covered this in the video, but you can perfectly use this as well. So I also have a very nice, in my opinion, really one of the nicest around the YouTube and the literature, neuroadaptive control example in MATLAB. Watch also the MATLAB example of this video, that when you increase the number of neurons, number of radial basis functions on theta of x, you achieve a better and better system performance, which is expected by the universal function approximation theorem. As you include more basis functions, more neurons, you get better performance. And then I introduced one of the very best performance recovery methods, and this is, in my opinion, one of the most important videos that I have uploaded to date to YouTube on adaptive control. Basically, it addresses potential poor performance that can happen due to many reasons. Let me fill this up. Many reasons can be, for example, let's say you are using a sigma modification or leakage modification, you choose this to be high. If you remember from the example videos that I upload on leakage modifications, so if you choose it to be high, then this part of the adaptation will be dominant, which will basically, if you look at this equation, leakage, it will basically prevent you to adapt. So your weights will try to converge. This part will make your weights to converge to 0. This part will try to adapt. There is a conflict and you are going to have a poor performance. Performance recovery addresses that. So let's say if you incorrectly choose that, performance recovery will address this drawback. Or let's say, instead of choosing many neurons, you choose in neuroadaptive control 4, 5, 6, 7 neurons. Your performance will be poor, yes, but performance recovery aspect will address that problem. So this is a very important video. If you haven't watched that, this is really practical and important video. I myself and my colleagues evaluated this performance recovery aspect in many real-world systems, and it works great. Otherwise, I wouldn't bother myself making a video out of it. All right, so what's happening in the performance recovery? You are adding a corrective signal here to the reference model and the control signal. It has this structure. The motivation of this structure, why we have this spatial form, it is not magic, it is controls, it is theoretical controls with applications to real engineering systems. The motivation behind this, I don't want to repeat myself, watch the performance recovery video. Basically, as you increase lambda here, the scalar parameter, if you choose it initially to be 1, if you make it 10, if you make it 20, eventually, as you increase it, you are going to recover the best possible performance from your system. So if you haven't, please watch that video. All right, so I summarized all the videos that I uploaded to this with regard to adaptive control, neuroadaptive control, neural networks, and learning. Now, we completed, if you watched all the videos up to this video, congratulations, you covered the basics, most important basics in adaptive control that we use currently today for real engineering systems. So what is next? Well, if you realized, I covered all videos with scalar dynamics. X dot equals to some uncertainty plus u. X was, one-dimensional, u was one-dimensional. Now, what is next? Obviously, we need to go from scalar to high-order dynamics, because almost all systems have high-order dynamics. And we are going to look at these type of systems. A, B are known. U is m-dimensional input, control input. X is n-dimensional, basically, state vector. And if you model, or if you control a system through moments, not through forces, almost all systems that you control, like using moments. For example, think about aircraft control. When you move control surfaces, then these basically generate a moment. So control actions generate moments to control pitch, yaw, and roll dynamics of the system, then basically you can put an aircraft easily into this form. And you are going to get more motivation, right? I'm going to dive more into detail, but basically we are first going to look at these type of systems, and I'm gonna cover now how to choose the reference model, how to choose the parameter update law. This is the W hat dot. We are going to cover structured and unstructured uncertainty cases for high order dynamics. We're gonna introduce neuroadaptive control for higher order dynamics. Likewise, these leakage and projection operator modification terms. And one of the drawbacks when you fly a vehicle, like there are a lot of things can happen, but for example, when you have icing on your basically control surfaces, your control will lose its effectiveness. In this case, B can be unknown. Its effectiveness can get reduced. So we are going to look at the practical case, what happens if B is unknown. In the literature, it is called, the unknown B case is called as unknown control effectiveness case. We're gonna look at this. We're gonna look at performance recovery for higher order dynamics. And of course, you have nonlinear systems, and we are going to look at more nonlinear stuff for higher order dynamics. I mentioned you guys probably before, either in a video or through the email or Twitter. Basically, I am also very research active and working with a lot of people, teaching in a university, composing musics and doing all other stuff. So I will try to upload most of the stuff, but sometimes it can be slow, sometimes it can be fast, so bear with me. Also, new semester is about to start in United States, so bear with me. I will cover everything. The best is subscribe, so that you will get alerts when there is a new video. I generally tend to upload videos at least a week on Sunday, or sometimes 2 times a week on Thursdays and Sundays. But sometimes there is a travel, I forgot to upload, or other stuff, other commitments I need to look at. So if you subscribe, it will be the more best healthy way how you get alerts about if I upload a new video or not. All right, so these are the stuff that I'm planning to cover, most of it at least, next. And in the very first video on this playlist, I mentioned some prerequisites. Now, I would like to mention prerequisites now more specifically for the next upcoming material that I am going to cover on high order adaptive control model, reference adaptive control. So this is another playlist on my channel, lectures on advanced control systems. I will suggest, as a control engineer, if you deal with controls, you should watch and know all of them. So all the videos that I upload here or will upload here are important based on my experience. And these are the stuff that almost I used most of the time. So from the modeling, I will watch for sure state space representations. Again, this playlist has 27 videos. I am going to highlight the really 7 videos you should watch before watching the next content. Otherwise, you may have difficulty in understanding some stuff, but if you watch these 7 videos, we will be on the same page. I promise you, we will be on the same page. We started using Lyapunov stability a lot, but I really like this video. It is really to the point video that discusses the Lyapunov stability and more. Likewise, eigenvalues and more. State and output feedback control of linear systems. These videos has nothing to do with uncertainties or adaptive control, just the basics. And I really recommend that you watch this video as well. And these 2 videos are 2 ways that we use pole placement and optimal linear quadratic control. When we try to make a matrix Hurwitz, or a stable matrix, we use these 2 methods. Please watch these videos, very important. And when later we dive into the nonlinear stuff, you should watch gain scheduled control video. I think that this is a really powerful approach when you deal with a real nonlinear system. So you should also watch this video. You don't need to watch it right away, but schedule to watch. Probably you don't need to watch for the content that I'm going to upload for the next couple of months, but at some point we are going to touch gain scheduled adaptive control, gain scheduled model reference adaptive control, so you should also watch these videos. As this being said, thank you very much. I have received many comments to the previous videos, many emails, and thanks for your support, and I really enjoy that dealing. Basically, I really enjoy interacting with you through the comments, emails, and through Twitter. And take care. So see you in the next model reference adaptive control videos when we deal with high order systems.